Okay, so now let's talk about pre-calculus and limits. So let's relate what you know from pre-calculus to what you are learning about limits. And so you'll have a function. So here's that graph from before. You'll have a function, and then you'll be asked, what is the limit as x approaches infinity or negative infinity of, and then the function is right here. So I'm going to say of x over x squared minus 1. Now, you've done this graphically, so let's go back to that. If I look on the graph, as the x values approach infinity, which are over here, the y values of the graph approach and get really close to the asymptote, this horizontal asymptote. So I would say that as the x values approach infinity, the y values approach the asymptote, and I just so happen to know that the asymptote is y equals 1. So as the x values approach infinity, the y values approach 1. And then if I were to go the other direction and find the limit as x approaches negative infinity of the same function, if I were to try to figure out what that was, I would look at the other side, at the negative infinity side of the graph, and as the x values approach negative infinity, the y values also approach the horizontal asymptote. So I would say that the limit as x approaches negative infinity of x over x squared minus 1 is equal to 1. Now, it just so happens that my limits at infinity and negative infinity are the equation of the horizontal asymptote. So if you know how to find a horizontal asymptote from your pre-cal skills, and then you're asked to find the limit at infinity or negative infinity in calculus, then you can use the skills that you learned in pre-cal about asymptotes to figure out the answer to the limit question. So it's kind of the same, except they're just asking you, the question is just a little bit different. So let me show you what I mean. Again, here's the cases we talked about in the last video, so you can refer back to that video if you want to know those equations again, or those cases. But if you look on page 23 in your notes packet, the one that you picked up from school, you'll have this situation, and we're looking at limits. Now, these are just some random graphs just for illustrations that we're going to have asymptotes we're looking for. The graphs are not the problems, or maybe not necessarily the problem. So let's evaluate this limit. So on number 6, I'm looking for the answer to the problem. What is the limit as x approaches infinity of 4x minus 3, I'm on this one, over 8x plus 1? Well, if I think about the equation y equals 4x minus 3 over 8x plus 1, and I want to know where the horizontal asymptote is, well, I know that the degrees are the same. So there's a horizontal asymptote at y equals 4/8, which is 1/2. But the limit as x approaches infinity is asking, what's your graph doing out at the end, out on the right side? Well, it's approaching an asymptote, and the asymptote is 1/2. So I just say 1/2. So you can find the asymptote, then you can find the limit. For 6b, if I think about the function y equals 6x minus 7 over x squared minus 3, I notice that the degree in the denominator is larger than the degree in the numerator. So that tells me that that function has a horizontal asymptote at y equals 0. So when I go to evaluate the limit as x approaches negative infinity of this function, what's happening on the left side of the function? The function is approaching the horizontal asymptote, which is 0. Hey, don't have to do any math. I just have to look at the function. Now, 6c is saying, what is the limit as x approaches infinity? And so in this case, if I think about the function y equals 2x to the 4th over 5x cubed plus 1, then I know that the degree in the numerator is larger than the degree in the denominator. So that tells me that this function has no horizontal asymptote. Well, if it doesn't have a horizontal asymptote at the end, like if it doesn't approach anything at the end. So if I think of a function that doesn't have a horizontal asymptote, like a parabola. Parabolas don't have horizontal asymptotes, so they'll either approach infinity or negative infinity. Lines will also only approach infinity or negative infinity. Or if I think of cubic functions, those only approach infinity or negative infinity. So if a function does not have a horizontal asymptote, I might want to write this down. If no horizontal asymptote, then it will either approach positive infinity or negative infinity. So you just have to figure out which one. And if I know the answer regardless is going to be an infinite limit, I'm really just worried about, is it going to be a positive number or a negative number? So I just am going to think in terms of positives and negatives. So I go back up to my function and I start thinking about it. I think, okay, so the top is 2x to the fourth, and I'm approaching positive infinity. Well, positive infinity is a really big number, so I'm just going to generally think about this. So if I take 2 and multiply it times a big number raised to the fourth power, well, a big number like 1,000,000 to the fourth power times 2 is positive. Okay? And then in the denominator, I'm going to take 5 and think about substituting in a really big number like 1,000,000,000, cubing it, multiplying it by 5, and then adding 1. Well, if I take like 1,000,000,000, cube it, multiply by 5, and add 1, that's still going to give me a positive number. And then a positive divided by a positive is positive. So the limit as x approaches infinity of this one is positive infinity. So you can keep the asymptote rules, but then if there's no asymptote, then you just have to figure out, is your answer going to be positive infinity or negative infinity? All right, so that's what we have in our notes. Let me show you what it's going to look like in Delta Math. So here's an example. You'll have one like this. Determine if the limit exists or not. And let's see, if I look at this, the limit as x approaches infinity, the degree on the top is equal to the degree on the bottom. So I'm going to say that this is equal to, there's a horizontal asymptote. Get my pen ready. There'll be a horizontal asymptote at y equals the leading coefficients, which is 3 over 18. And 3 over 18 is 1/6. So then the limit as x approaches infinity, the y values are going to approach 1/6. Let's see, another example from Delta Math. Sometimes they'll have you multiply it out first. So let's do that. Limit as x approaches infinity, multiply the numerator, 12x squared minus 8 over denominator 4x cubed plus 8x to the fifth minus 3 minus 6x squared. Okay, then I'm going to know, let's see, my degree on the top is 2, degree on the bottom is 5. So the degree on the bottom is larger than the degree on the top, which means there's a horizontal asymptote at 0. So my limit as x approaches infinity will be 0. And then you'll have some that ask you to go back to your notes, radicals. And you'll do them the same way, but you'll have to consider the radicals, okay? So let me zoom in on this one. Nope, I can't zoom in like that. I forgot. I have to zoom in this way. Otherwise, my pen goes away. Okay, so now I'm looking at this. I can still use the idea of comparing the degree of the numerator and the degree of the denominator, but I have to take into consideration the radical. So if I were to compare straight up, I would just compare like the degree of the x and the degree of the x, but the problem is this x is under a radical. So what you'll do for these are you're just going to think of it as the only term that's going to be irrelevant is the term that would have the highest exponent. So this 1 is not going to be relevant because we're thinking about substituting in really, really large numbers or really, really small numbers. And at the end of the day, if you're going to substitute in a really small number, then that 1 is not going to make a difference. Because if you think about like negative a million plus 1 versus negative a million plus 2 is still pretty much the same value. So when you're evaluating these, you can just worry about comparing the highest number under the radical, or the highest degree term under the radical. So I can think about this as being the limit as x approaches negative infinity of the square root of negative x over x. And then I go and I compare the degrees. Well, the degree of the denominator is 1. The degree of the numerator under the radical, that's 1. But then if I were to take the square root of that, it would be like dividing what's that exponent 1 in half. So the degree of the numerator is more like a half, and the degree of the denominator is 1. So I have a function where the degree of the denominator is larger than the degree of the numerator. So in this case, that would mean that I have the limit as x approaches negative infinity of the square of the whole thing, 1 minus x over x. Since the degree of the denominator is larger, then there's a horizontal asymptote at 0, and the limit approaches 0. So in the second one, I'm going to only compare the parts that have the highest degree. So like I'm going to compare this one, I'm going to compare this one. So I'm going to think of the limit as x approaches infinity of the square root of x squared over 2x. Well, the degree of the numerator, under the radical it's 2, but when you take the square root of it, it gets divided in half. So that means the degree of the numerator is 1. The degree of the denominator is also 1. So now I'm going to compare the leading coefficients. Well, the leading coefficient in front of the x squared is a 1. So there's a 1 right there. So the square root of 1 is 1 over 2. So this equals 1/2. And then one more like that. If I look at only the relevant terms again, the degree of the numerator, divide that x squared, divide that 2 in half, and I get 1. So the degree of the top is 1. Degree of the bottom is 1. So I'm going to be looking at the limit as x approaches negative infinity of the square root of x squared over 2x. And so this time, let's see, I'm thinking about the leading coefficients. So the ratio of the leading coefficients is 1 over 2. But we do have to be careful when you approach negative infinity, because you have to think that you're going to be substituting in negative values. Like if I were to evaluate this thinking substituting in negative values like negative a million. Well, if I put negative a million in the numerator, negative a million squared and then square rooted is still positive, because whenever you square negative, it becomes positive. So the numerator is still positive, but the denominator, if I put a negative number in for that x, I'll end up with a negative. So we do need to consider the sign. A positive divided by negative is a negative. And you'll only have to worry about considering the sign if your limit's approaching negative infinity. And so then you'll have some in Delta Math that do the same things. but they'll look a little more complex. But again, you're only going to compare the relevant, the terms that have the highest degree. So I'm only comparing here and there. So the degree of the numerator is 3, not 3. Yeah, divide 12 by the index. So 12 divided by 3 degree would be 4. Degree here would be 4. And so if I think of the leading coefficients, I've got a 27, but it's being cube rooted. So the cubed root of 27 over 7. The cubed root of 27 is 3 over 7. So 3/7. All right. Good luck with this. If you guys need help,